I'm working from home today. Okay. Now, just to remind you, last session we've been talking about application. We discussed the uninterruptible power supply, the disturbances, how we use power conditioner to make sure that the power quality will be high enough for our loads. Today I will talk about some residential and industrial applications. Just to remind you, the industry in general, if we look to the industry, we are talking about motors, we are talking about ovens and light. These are the main, and mainly talking here about inductive loads. So in this part, we're going to talk about induction heating, welding, lighting, how we control them using power electronic converter, the one we just discussed in our semester. And it's also good to highlight here that why will we let me say design our new technology to fit our lifestyle, our requirements and need. We need to consider a few important things. These are the energy conservation. We need to conserve energy. We need to do the same function with less energy consumption. This is what we call energy conservation. Usually I talk with students in level 4 in renewable energy about energy conservation. Also, we need to reduce the cost. Cost is an issue. Economic side view is an important, let me say, element we need to consider. Reducing the cost is one of the things researchers do, research and development, to make the prices going down. Also, we need to increase to the safety and the greater comfort. How can we do this, and where we are going to do this? We are going to do this in many applications we are dealing with at home, in our offices, in the companies, in the industry. Okay, you know, when we go there, the applications, the appliances we deal with is space heating, air conditioner as example, heating for in cold places or cooling in hot places. Also heating water, refrigeration, let me say lighting, cooking, television, and many other appliances. Okay, now I will pick some examples here in our discussion today for the applications, and I will start from the air conditioner. Now, air conditioner, the technology we are using here is old, actually, bit technology, talking about 50 years back technology. Many countries are not using this type of technology, but still we are using this technology here in this region, in the Middle East. Why? Because this technology consumes huge amount of energy just for cooling. We can't cool with this energy. There are many other ways. I'm going to talk with you, inshallah, next year in level 4 about these technologies. But now, let me just explain to you how the air conditioning work. Air conditioning, simply, we have motor compressor, and there is gas inside. And then they compress the gas will rotate in a pipes. When it rotates in a pipes, it get cooling the pipes, which is from copper, let me say, or metal. And then I have another fan, which blow the air. Then the air will get cooled when it go through these pipes. Okay. Now, what is the problem here? The problem is this motor compressor absorbs a huge amount of current, large current, and huge amount of energy and power. I mean, talking about between 10 to 20 ampere, 20 to 20 ampere when we talk about 220 or 230 volt, we are talking about around 2,000 to 3,000 watt, which is huge. Okay. Now, this air condition work based on a sensor which is called thermostat. Thermostat of the compressor, it senses the temperature. So if it is go down or above the range required, as example, we fix the temperature on 23 Celsius. I know some of you maybe make it 18 Celsius or 19, but the better is to 23, 24 in this range. Anyway, this thermostat will switch on and off the motor and the compressor. And when it switches on and off, what happens is the motor, you know, when it start running, okay, start running, it's observed 5 times the full load current. You got it? Which is not good. So how can we prevent the motor from keep running, I mean, start on and start off? By using what we call it, by the way, don't forget, we will use here, have a look, we will use adjustable speed drive, or we call it sometimes variable frequency drive. It is the box discussed before, the one which is rectifier, and then capacitor here, and then we have inverter. You remember this? This we call it variable voltage source inverter. We have rectifier here. We have inverter here. These two together, we call them ASD or VFD. Here is the variable frequency drive. How it work? It work in this way. Have a look. You see here we are switching on, switching off the normal one, and the current increase gradually. Okay, so this is the conventional heat pump. The new one, no, we are going to use programmable let me say thermostat. How? Have a look. We make a range for the temperature, let me say. So when the temperature going up, it means get heated, we want cool, so we need to move the gas. So what we will do, we will observe more power. Okay, so it get cooled and the temperature reduce. Now when it get cold, we need to what to do to reduce the observed current, so the temperature increase. So in this way we are keep fluctuating in this way here. In this way we don't need to switch on and off similar to this here. Switch on, switch off, switch on, switch off. We don't need this. We keep controlling it. How we control it? By controlling the VFD here. We control the operation of the pulse width modulation for the inverter here. Okay, pulse width modulation, different techniques we use. And then we control how the motor will work. In this way, we don't need to switch on and switch off. In this way also, we reduce the energy conservation. What type of circuit we use? Rectifier inverter, the converters, power electronic converters. Another example, lighting. We know lighting is available in our homes. Wherever we go, lighting is an issue, an important issue. Now, how lighting work? The conventional one, we have a blast, which is choke inductance at the end. And we have lamp here. Inside the lamp, there is gas. The choke will reduce the current observed current, but the voltage will be high, which makes spark. When it goes the spark through the light, through the gas, sorry, it get lighting. We see light coming, okay? Now, this is considered as a nonlinear load because it's not similar to Ohm's law, direct, let me say straight line equation. No, it is V square of the blast of the choke plus V square of the lamp equal to V source square. Now, how can we control the light? How can we control the light? Power electron cover is the best to control light. Give me example, I will tell you. By the way, these are the lights, as you can see here, double fluorescent here. This is the choke, different shape, okay? Now, how the two fluorescent lamp work? Okay, this is the choke here as a transformer, let me say. And we have here two lamps, A and B. Now, it seems to be this figure is more complicated. Can I simplify? Yes, I simplify it. It's look like here is better. Okay, have a look. Have a look. This is lamp A and lamp B. They are connected in series, right? And there is capacitor connected in parallel, which is called the startup capacitor. From the name startup capacitor, it means work only when starting, and then it's gone. And there is another capacitor which is called CPF, which is power factor correction capacitor, connected series. It's from the name clear that it corrects the power factor. Why it's correct the power factor? Because we have inductance in the circuit which observe reactive energy. It means the power factor will go down. With capacitor, it will produce reactive energy, it go up. So we compensate, let me say. And this is my inductance, as you can see here. Let me tell you how it works. When we switch on, at the beginning, the capacitor here, startup capacitor, will be short circuit until it gets charged to become open circuit. When it's short circuit, the lamp B will be connected to a short circuit in parallel, so it is not there anymore. So the whole voltage will apply where? On lamp A. So lamp A will trigger and light will coming and current will follow. This is happening at the beginning. Then this is charged. The voltage now apply across lamp B. So lamp B also will spark and then light will come on and then we continue. The capacitor here will keep providing the required compensation for reactive power. Okay. Now, until now, this is the conventional how it work. Okay. What we want to know, how I can use power electronic to control this lighting application. Have a look. We can control the lighting by using high frequency electronic blast. What high frequency electronic blast is? We have the inductors. We control the applied voltage by controlling its frequency. Increase the frequency or reduce the frequency will increase or decrease the light coming from the lamps. Now this circuit here, from where it came from power electronic converters. Oh, can we change the frequency? Yes, inverter can change the frequency. Cyclo converters can change the frequency, and so on. How it look like this circuit? Have a look. We have rectifier, capacitor as a smoothing. We discussed rectifier, the power electronic converter is called rectifier. We discussed the DC to high frequency inverter, half a bridge, full bridge, push-pull, any one of them. At the end, the output have high frequency. So if we control this high frequency by controlling the inverter through pulse width modulation, we control the light. And this is what we are looking for. I talked about air conditioning, how we use variable frequency drive to control it. I talked about lighting, how we use high frequency inverter to control it. Let me talk about induction cooking. Let me start. By the way, when I say induction cooking is small, but we can apply, it's applied already there in the industry, but large scale. This is a small scale. Let me show you how it works. Here we have a metal pan. It's a metal with a cover. It's like in Arabic they call it tanjara, right? They cook in it inside it. It's from metal, okay? And there is inductance here, as you can see here. Distance between them is small. And we need here rectifier again with high frequency inverter, the same previous circuit. Now this produce output here coming to the inductance with variable frequency, high frequency, talking about 10 kilohertz, 20 kilohertz, 40 kilohertz, and so on. When it go through this, let me say inductance, it's like behave like a microwave heat. It will produce, according to Maxwell, it will produce a magnetic field surrounding this inductance. And this magnetic field surrounding the inductance, when it gets cut for the metal panel, okay, metal pan, it will produce current inside. Here inside the metal, it will produce current. This current called ED current, if you remember, okay? So when it's produce current and the metal, it have a resistance, then what I have, I square R. What is I square R? Heat. So I get heat the metal pan. Increase or decrease the heat depend on the frequency also. Okay, on the distance, on the frequency. How this happen? It happen either, you see here, this is the diode circuit, this is the inverter circuit, and here the induction coil connected in series, or they sometimes connected in parallel. The same previous circuit but connected in parallel. Now the heat increase or decrease based on the current, as I mentioned, I square R. But the current itself is a function of IO, which is the current surface on the metal pan, multiplied by exponential minus X. X is the distance between the pan and the coil, and delta is the penetration depth. It means depth inside the metal. But this delta actually is a function of K is a constant, rho is the resistivity of the metal, but of the frequency. So you change the frequency, you change delta, you change the current, you change I square R, you change the heat. You got it? How we control it? All this to be done through what? Through our power electronics converter, rectifier and inverter, as we discussed before. And by the way, these are the applications available in industry. If you go to industry, you will see these. Okay. Now this is another application, which is welding. You can see here heating or welding or induction heating. Okay. How welding work? Welding work in this way. We have here transformer for isolation because we're gonna work because we're gonna do short circuit. We have metal. We do short circuit. I square R will melt the metal, and then we have welding. So here, stepping down transformer, a conventional one line frequency transformer. And here we have thyristor controller bridge, inductance, and then we have the output. Sometimes what they do, they use bridge rectifier, no thyristor, diode rectifier, uncontrolled one, which is already discussed before, with a series regulator. Semiconductor switch, it could be thyristor, triac, diode, whatever it is. Or we may use diode bridge rectifier, okay, with switch mode DC to DC converter. It could be buck boost, Coke converter, any one of them. At the end, we make melting by I square R, and then we have welding. These are different type of welding. I think you already saw this somewhere. I mean, either outside. I mean, it's clear, but it's working as a short circuit, and power electron converter is the main part of this process. For switch mode welding, what they do sometimes, they try to, because they want control, they use rectifier, capacitor, inverter, okay, and then transformer, high frequency transformer, and then diode rectifier to rectify again. But they make the control here. All this process just to control the output. They control it from here. This one better than the conventional one, because here we have more control on the welding. Another also way to control heat is by using AC voltage controller. You remember we discussed AC voltage controller. We discussed the on-off controller and phase shift controller. You remember for on-off controller, we mentioned that we're gonna switch on for a few cycles, and we're gonna switch off for another few cycles. This is good to control, but to produce heat. For that, it is not advisable to use it to control motors, okay? Because it heats the winding, it's burning the winding, it's oiling the windings, so it's not preferable. So what we do here, we use this type of controller to control the thermal system, okay, heat system. As example, oven, induction oven, not induction oven, normal oven. You see here, these are some pulses on, and then sometime off, and again on and off. In this way, we control the output. We discussed this already before. Now, let me summarize before I finish this session. First, for application, we discussed the uninterruptible power supply, okay? And then we discussed the use of power electron converters in different stages of this power supply. And then we discussed the use of power electronic converters to reduce the impact of disturbances. Different type of disturbances have been discussed, okay? And then we talked today about using power electronic converters to control the air conditioning, the lighting, the induction heating, the welding. These are samples of power electronic converters applications. Otherwise, they are more than this, but as I just gave here samples of their applications. Now, I think I still have next week, inshallah, the session. We will talk about using power electron converter to drive electrical machine. How we can drive them, DC machine or AC machine, different type, okay? And you know that machine is, let me say, crucial element in industry. Without machine, there is no dynamic, let me say, process. It will be static only. And the industry look to have machine. At home, we have machine in our equipment, washing machine, or let me say refrigerator, air condition, all of them contain machine. So I stop here. Do you have any question before I leave?